Hey everyone, welcome back to the AHA Method. I'm Johnny, and today, you are an astronaut. Your capsule is right here, and the space station you need to dock with is right there, a little bit ahead of you, on the exact same orbit. Your job sounds simple. Catch up to it and dock. So here's my question, and I want you to actually answer it before I say anything. To catch something that's ahead of you, what do? You speed up, right? Fire the engine forward and close the gap. Lock in your answer. And on a highway, that's obviously right. The faster car catches the slower one, every single time. But up in orbit, watch what actually happens when you fire forward to catch the station. You drift up and away, and the station pulls ahead of you. You sped up, and you fell behind. That's not a glitch. That is how orbits really work, and it once caught a real NASA crew completely off guard. Back in 1965, on the Gemini 4 mission, astronaut Jim McDivitt tried exactly what you just did. There was a spent rocket stage floating near his capsule, and he tried to fly over to it, point the nose at it, thrust toward it. But the harder he chased, the more it drifted away and dropped below him. He burned through fuel and had to give up. Afterwards, the crew admitted they just hadn't reasoned out the orbital mechanics. Nobody really had yet. The fix came from a man nicknamed Dr. Rendezvous, Buzz Aldrin, who'd done his whole doctorate on this exact puzzle. Months later, Gemini 6 and 7 pulled off the first real space rendezvous, holding position barely a foot apart. So what did they understand that McDivitt's instincts didn't? Quick reset, because this is the key. An orbit isn't the station hovering up there. It's the station falling toward Earth forever, but moving sideways so fast that the ground curves away just as fast as it drops. An orbit is perpetual falling. Hold on to that, it explains everything. Here's what I want you to guess. 2 orbits, one low and one high. Which spacecraft is moving faster, the low one or the high one? Pick one and comment it below. And to actually explain this, who better than the man who worked out how orbits work in the first place? Let's bring in Sir Isaac Newton.
Ah, orbits. I confess a certain fondness for this one. Let me tell you about a cannon. Imagine a cannon on a mountaintop, impossibly tall. Fire the ball gently, it arcs down and lands nearby. Fire it harder, it lands farther. But fire it hard enough, and something wonderful happens. The ground curves away beneath it exactly as fast as it falls, and it never lands at all. It falls around the whole world.
So an orbit is really just falling sideways fast enough to keep missing the ground. And how fast you throw it decides the whole shape of the path.
Precisely. Now let us reason it out. Gravity is the string that keeps the ball turning. Set gravity equal to the pull needed to bend the path into a circle, and solve for the speed. Look what falls out. The speed depends on your radius. The lower you orbit, the faster you must travel. See it move. The inner satellite races, the outer one crawls. The station, low down at 400 kilometers, laps the entire Earth in about 90 minutes. The moon, far out, takes 27 days.
Whoa, so closer in means faster? That already feels backwards.
It gets better. How long a lap takes, the period, grows with the size of the orbit. I proved this from my law of gravity, what Kepler had only observed. A bigger orbit means a longer lap. Hold those two facts together. Lower is faster, and smaller laps quicker. Now, McDivitt's instinct. When you fire your engine forward, you don't simply gain speed. You add energy, and energy sets the size of your orbit. So firing forward swells your orbit into a bigger ellipse, climbing away on the far side. And a bigger orbit, we just said, takes a longer lap. You rise, you slow your lap, and the station sails ahead of you.
So that's what happened to Gemini 4. Every time he chased it, he was climbing into a slower lane and falling behind.
The whole chain, in one line. Speed up, add energy, bigger orbit, slower lap, fall behind. So do the opposite. Fire backward. You shed energy, drop into a lower, smaller orbit, and by our rule, a smaller orbit laps quicker. You sweep around faster and overtake the station.
Wait, so I slow down on purpose, drop lower, and that's what lets me catch up? That is so weird.
And here is the twist inside the twist. As you fall to that lower orbit, You actually speed up, trading height for velocity. You braked for an instant and thereby fell into a swifter orbit. The chain again, the other way. Slow down, shed energy, smaller orbit, faster lap, catch up. Then, once you've pulled level with the station but riding below it, one gentle push forward lifts you back up to its height, matching its speed side by side, and you dock. There is the whole recipe. Slow down to drop, catch up from below, speed up to rise and dock. Here is the lesson beneath the lesson. On a road, your throttle sets your speed. In orbit, it does not. Your throttle sets your energy, energy sets the size of your orbit, and the size sets how fast you lap. You are not steering a car. You are choosing which orbit to fall around.
So you fire the brakes and you end up moving faster. My highway brain is completely perfectly backwards up here.
And this is not a museum piece. Every cargo ship and every crew that visits the space station does exactly this. It launches into a lower, faster orbit and chases the station from behind and below, gaining a little each lap, then rises the last step to dock.
So the whole world does the backwards thing, because the backwards thing is the right thing. Okay, one fair question. Is my highway brain ever right up here?
At the very end, yes. Once you are a few meters apart and matched in orbit, the great falling all but cancels, and a gentle nudge behaves much as it would on your road. The paradox rules the long chase. Simple pushing finishes the kiss. This tidy picture also sets aside a couple of real burdens, tilting the orbit's plane and waiting for the right moment to launch. But the heart of it is exactly this.
So if you were the pilot, how many laps would you ride that low orbit before rising up to dock? Too few and you undershoot. Comment your call, I actually want to know.
2 lessons today, my friend. First, an orbit is falling, and it is energy, not throttle, that sets both your speed and your lap time.
And second, when the instinct from one world gets dropped into another, trust the physics over the feeling. That's exactly where the real understanding was hiding.
Keep wondering, keep questioning.
Thank you, Mr. Newton, and thank you for watching. If this made orbits finally click, hit like and subscribe. It genuinely helps the channel. See you in the next one. Goodbye.